right, so now we've reached the top of the hour. Hello, everybody. My name is Martin Clay with Blue Physics, and today our webinar will be on plastic scintillator detectors and small field dosimetry. Well, thank you again for joining us. As I mentioned before, the questions and answers session will be at the end of the webinar, and so if you have a question, please put it in the Q&A section. And so with that, please allow me to introduce Blue Physics founder and CEO, Marcus Viejo.
Thank you, Martin. Thank you for the introduction, and thank you for organizing this webinar. This presentation is about Blue Physics, about our technology, a little bit about our company, and especially focus in our small field dosimetry functionality. Martin, only just to be sure, can you see my screen correctly, correct?
Yes.
Okay, good, thank you. Okay, so let me first introduce myself. My name is Marcos Feijóo. I'm the CEO and founder of Blue Physics. I'm a physicist, a theoretical physicist. I'm not a medical physicist. I'm originally from Spain, but I've been living in the US for the last 20 years. All my experience in radiation therapy is basically based in working for companies like Computerized Medical Systems first, and then was acquired by Elekta. So I ended up working for Elekta for more than 18 years. I'm very pleased to tell you that we have a huge and a very good team behind Blue Physics. I would like to emphasize a couple of names in our org chart. Of course, Martin Clay, who is our USA sales director, organizer of this series of webinars, and the person you can contact if you are interested in knowing more about our technology, or if you want to see a demo of our technology. So we have a big group of salespeople around the world, but I would like to emphasize the medical physicist collaborators we also have around the world. I would like to mention our close collaboration with Dr. Williamson and the rest of the Virginia Commonwealth University. I would also like to emphasize our collaboration with Dr. Indra Das from Northwestern Medicine, a world opinion leader about the small field dosimetry. I also would like to emphasize our close collaboration with TRS 483 experts around the world, like Professor Rodolfo Alfonso from the International Atomic Energy Agency, who is one of the co-authors of the TRS 483, and also Professor José Lárraga from Instituto de Neurocirugía and Neurología of Mexico, also a world expert in the TRS 483 and small field dosimetry. So now let me tell you a little bit about why we established Blue Physics already 9 years ago. It's because when I was working by Elekta, I realized that linear accelerators are evolving tremendously lately. We now have linear accelerators for radiation surgery, like this one sub or CyberKnife or Gamma Knife. We have linear accelerators with magnetic resonance, MR-Linacs, like Unity from Elekta. We have proton machines delivering protons and particles. We have also new flash treatments that are under investigation but are very promising. But when I was in Elekta, I was thinking about how we are measuring radiation in with this new technology. And I realized that we are still using ion chambers and diodes. That is basically technology we have been using for the last 100 years. And it has not evolved in the same way linear accelerators or delivery machines have evolved. For example, ion chambers and diodes are either too large for a small field dosimetry, or they are not equivalent to human body tissue. They are not equivalent to water. They are not fully MR compatible. You cannot take, for example, MR images while these detectors are in an MR linac. And very important, they are very slow. And in today, with the proton therapies and flash therapies, we are really looking for detectors that are that have a very high time resolution. So I was thinking about all those things when I was working for Elekta, and I took the decision to quit my job at Elekta and start developing a new technology to measure radiation in a totally different way that will overcome all the limitations of the current technology available in the market. It took us 7 years, but we are very proud to tell you that now Blue Physics has a total finished product. It is commercially available. It is FDA registered, and we are currently commercializing this technology. Also, very important aspect is in Blue Physics, we have developed everything from end to end. We have developed the detectors, the optical fibers that transport the light signal from the detectors to the acquisition unit. We have developed all the acquisition unit, including the optical parts and electronic parts, and the digitizers that digitize that information and shows the data in the software that we also have developed in real time. So now let me tell you a little bit of the secrets of our technology. And let me start with the detectors itself. The detectors are plastic scintillating sensors, are cylinders of only 1 millimeter diameter and 1 millimeter long. You can see here, this small cylinder, black cylinder, is the detector, is right next to a penny. Just to give you an idea of the little size of our detectors. The sensitivity volume is only 0.78 millimeters cubics, and they are water equivalent. These properties make those detectors ideal for a small field dosimetry. Our technology also allows for easy scale to multiple detectors. Right now, we are offering systems with 1 detector, 2, 4, 8, and we are now planning to do more release with many more detectors. So we can develop systems of phantoms with many of those detectors distributed even in 3-dimensional arrangement. Here you can also see a microscopic view of the detector. As you can see, it's a 1 millimeter long and 1 millimeter diameter. Although we are now making detectors even smaller, of only 0.5 millimeters long. Plastic scintillators have been around for many years, so I'm not discovering anything when I tell you that the way plastic scintillators work is that when they receive radiation, they emit light, visible light, blue light, when they receive the radiation, and that amount of light is proportional to the dose they are receiving. So the only thing we have to do is to analyze, measure that light, and we will be measuring the amount of dose delivered at every given moment. So we are attaching a transport optical fiber that will capture the light coming from the detector, and it will be transported all the way outside the bunker where our acquisition unit will be located. The transport optical fiber will also emit some kind of light through due to the Cherenkov effect. The radiation will accelerate the electrons in the optical fiber, and the electrons will travel faster than the speed of light in that medium. That will produce a characteristic light. It's called Cherenkov. Cherenkov effect is nothing more like a cable effect that many other detectors have. We have to subtract that Cherenkov effect. And the way we chose to subtract the Cherenkov effect is a very simple and very direct way. We simply put a second optical fiber, adjacent to the first one, identical to the first one, but not connected to the detector. That way, we can measure in real time the Cherenkov effect, and we can subtract that in real time. Very easy way to subtract Cherenkov that allow us to have scale multiple detectors systems very easily. Another secret of our technology are the optical fibers that transport the light signal from the detector to the acquisition unit. First of all, they are very thin. They measure only 0.25 millimeters diameter. That allows us to bundle many of those fibers in a single jacket, in a single cable of only 3 millimeters diameter. When we have multiple detector systems, that is not a bulky arrangement of multiple fibers because they are so thin that they all fit perfectly in a jacket of only 3 millimeters. Another big advantage of these fibers is that they are up to 20 meters long. That allows us to put all the electronics and metal parts of our system outside the bunker. In the bunker, we only have water equivalent materials. All the electronic parts and metal parts are outside the bunker. About 3 years ago, I quit my job at Electa. I started traveling around the world showing this technology. One of the first hospitals that opened the doors, it was Hospital Universitario La Paz in Madrid, where they have an MR Linac. They extensively test our technology, and they make this publication in Medical Physics. This publication is available, and this publication contains all the characterization of our detectors when compared with conventional detectors. I strongly recommend you to download this article from Medical Physics, where you will be able to find multiple characteristics of our detectors, comparisons with the current detectors available in the market, output factors, PDD, profiles, temperature dependencies that we have proved that it is not dependent in temperature, or energy dependence that we also prove is not energy dependent. All the information you may be asking yourself about the quality of our detectors can be found in this article. We are also very proud to have a good relationship with Dr. Indra Das from Northwestern Medicine. Dr. Indra Das and his team are experts in small field dosimetry. They have also acquired our systems and tested it very thorough. And they have proved that blue physics detector is ideal for small field dosimetry, and it does not require correction factors. Dr. Indra Das and his team, they have made multiple publications in the past AAPMs and ASTER conferences, also publications in Medical Physics. Their conclusions are overwhelmed for us because they are admitting that our technology is ideal for small field dosimetry, and they are also very impressed with the speed of our detector. We have many more publications and many more posters and abstracts presented to different conferences around the world. What I'm trying to say in this with this slide is that our technology has been very well tested and proved that it works and it measures radiation correctly by world opinion leaders around the world. But our detectors and our technology are not only ideal for small field dosimetry and fully MR compatible, they are also very fast. We can measure radiation at a speed, we can take samples every 300 microseconds. And let me give you an example what it means. This is a video of our detector measuring a conventional Linac 100 monitor units. But when the measurement finish, we can do a zoom and we can show you the dose delivered by every single pulse of the Linac. We can tell you the number of pulses delivered. We can tell you the dose delivered by every single pulse. This allows us to take pictures like this or to take measurements like this. This is a measurement of a single monitor unit treatment done with a variant Halcyon Linac, but it can be repeated in any other Linac. And again, this is only one monitor unit treatment. And we can not only measure the dose delivered by that monitor unit. We can also show you and tell you the number of pulses that has been delivered, in this case 12 pulses, and we can tell you the dose delivered by every single of those pulses. And that first pulse is a little bit lower than the rest. Believe me, is nothing wrong with our detector. It is the linac, is the way linacs work. The first pulses are normally a little bit lower than the subsequent pulses. Let me show you a similar picture done in a different linac, in this case in a sub-linac, a specialized radiosurgery linac. And here you can see that when we deliver one monitor unit with this new linac, it is 31 pulses, and here you can see the dose delivered by every of these pulses. This high time resolution allows us to do things like this. We can plot and monitor the dose, the dose delivered by shots of 100 monitor units. So here you can see 5 shots delivered by a sub-linac, 100 monitor units each shot. We can see how the ramp up, we can measure very well the ramp up of the dose delivered by the linac. And we can see perfectly that the first shot had a larger ramp up than the subsequent shots. Another important aspect of this plot is that the noise you see is not the noise from the detector, these are the pulses from the linac. Also, the first 5 shots here are shots done with a cone of 25 millimeters, but the next 6 shots are shots done with a cone of only 4 millimeters. I want to emphasize how good is our signal versus the noise in a super small, tiny field of only 4 millimeters diameter. That extremely good signal noise ratio give us a big opportunity to do accurate measurements of super small field size, like only 4 millimeters. So again, we had a wonderful detector for small field dosimetry, and we started traveling around the world showing this technology. And I have to be very honest with you guys. At the beginning, in 2022, when I started showing this technology to centers with CyberKnife, for example, I have to admit I was a little bit frustrated, because even though we thought our detector was ideal for small field dosimetry, we could see that our measurements, output factor measurements, when comparing with current well-known detectors like diodes, we could see kind of like large difference when measuring with doing comparisons between blue physics and the diodes. It was only when we had compared with other detectors, and this time I asked these people, can we please measure with another detector? And they said, yeah, we have a microdiamond. Okay, why don't we measure with that microdiamond? And all of a sudden, the microdiamond was fitting better blue physics than the diode. But not only in this clinic, in many, many clinics I've been traveling around the world, also this one in Germany and in Portugal, we saw differences between blue physics, between the Monte Carlo calculations, in this case with SeisMocha, and other detectors like the microdiamond and microsilicon. To be honest, I was confused, and I didn't know what was happening. Why my detector, why all detectors are measuring different in a small field, for a small field dosimetry. Until I was lucky enough to meet these 2 gentlemen, Professor Rodolfo Alfonso from the International Atomic Energy Agency, and Professor José Lárraga from Instituto Nacional de Neurología y Neurocirugía de Mexico. These 2 gentlemen explain me how important is the TRS 483, is the code of practice that recommends the recommendations for small field dosimetry. Again, they proved to me that when we follow TRS 483 strictly, it is very easy to prove that blue physics not only is an excellent detector for small field dosimetry, it's also a detector that does not require correction factors for small field dosimetry. But again, it only can be proved when you truly follow TRS 483 recommendations. Since that point, we follow TRS-483 strictly in all the recommendations, not only correction factors, but also centering the detector, measuring field size, etc., etc. And following that, we proved that when we compare our measurements of a small field, as small as 4 millimeters collimator, our measurements are equally or even better than with any other detector, with the big advantage that we don't require correction factors. Professor Rodolfo Alfonso has been traveling around the world talking about small field dosimetry, talking about TRS-483, and we are very proud to say that he's recommending the use of blue physics as a detector that does not require correction factors for small field dosimetry. But small field dosimetry is not only about having a good detector. It's also extremely important to center the detector correctly and measure the field size correctly, following again TRS-483 recommendations. That's why with blue physics technology, we have developed software that will help to easily and rapidly position the detector in the center of the beam every single time and measure the field size. Let me give you an example. This is a video of our software measuring the dose in real time, and we can detect the center of the field because it's in the maximum. We can also identify the half of the maximum, and we can move manually the detector or automatically until we reach one of the edge. And then we go quickly to the other edge, passing through the middle. And when the red line touches the green line, we will know we are at the other edge of the field. So in few seconds, we can not only determine that we are placing the detector right in the middle of the dosimetric field size, we can also measure the field size in few seconds, going to one edge and to the other edge of the field half width maximum. And in few seconds, we can measure the actual field size and be sure we are placing the detector right in the middle, even if it's a super small field size of only 4 millimeters or even less than that. We have also developed new technology to do a end-to-end QA, especially for multi-metastasis tumors. We now have the technology to convert DICOM images of a particular patient in a 3D printing. We have the technology to be able to 3D print the replica of the head of the patient in few hours. But not only that, with the DICOM structures, we can 3D print tunnels where we will place several of our detectors, 3-4 detectors, in the exact position where the tumors are. You can even put the detectors in the exact position where the tumors are, or in a position where you want to see that no dose is coming, like you want to put in the center of an organ of risk. This allows us to have the only one system in the world that can do a full end-to-end QA with an exact replica of the patient head and placing the detectors in the exact positions where the multimetastasis tumors are. And it's cheap because printing one of those heads, it only costs about $7 in materials. It only takes few hours to print them out. It will be personalized for the patient. And guess what? At the end of the day, patient goes back home with a replica of his or her head as a proof that we have done a specific QA for that particular patient. And with that, I think I finished my presentation. I will be very happy to answer your questions. I'm also putting here our contacts, emails, and phone numbers. Feel free to contact us, contact Martin or myself for any question, or if you want to see a demo or you want to see our technology in action. And now, Martin, back to you. Let me know if there are any questions.
Yeah, thank you, Marcos. Do have a question. I don't mind his name. is John. John asked, how do you center the detector automatically? Do you have a motorized translation table, or is this in a water tank? Good question.
It's a very good question. Thank you for that, John. And the answer is yes. We can okay, let me come back to the picture. Let me come back to the picture. Yes. The centering and the measuring of the field size, we offer two options. Option number one, we connect the detector in the water tank, and then you move manually the water tank while you are visualizing the dose. And in few seconds, you can not only center, but measure the field size. In addition, we have just released a new version of the software that communicates directly with the PTW water tank, and we can control the PTW water tank from our software and get feedback from PTW water tank. And then we can do this operation you can see here. We can do that automatically with a single click of a button. So if you have any water tank, IBA, some nuclear, you can do this procedure manually in few seconds. If you have PTW water tank, you can do that manually or automatically with a single click of a button. I hope I answered your question.
Yep, thank you. Another question from Anthony. Is your 3D printed head phantom a release product or under development?
It's a good question. It's under development, and we offer two options here. We just offer the option to provide you the software that will convert your DICOM images to 3D printed images, and we will give you recommendations on what 3D printers you have to buy, and we will give you characteristics of the filaments you have to purchase with the characteristics of that filaments to do your 3D printing. It's an option we offer to customers to do their own printing of their own phantoms.
Okay. One more question. This is from Rodolfo. Do you plan to use the personalized phantom for PSQA for commissioning purposes or for both?
I guess PS means patient QA?
Yeah.
Yes, for the moment we are offering the technology to convert DICOM images into 3D printing and DICOM structures for the end-to-end personalized patient QA. We are open to any ideas about how else can we use this technology for other applications.
Okay. All right. At the moment, we have no more questions. And so with that, thank everybody for coming, and we will end